Hello and welcome to section 8.1.2 on solving 3x3 systems of equations. So what is meant by a 3x3 system of equations is that you have three equations, 1, 2, 3, and each of them has three variables at most. If one of the variables appears to be missing, it's simply that it has a zero coefficient. So these are all present in these three equations here. So the first three, the number of equations, 1, 2, 3. The second three, the number of variables, 1, 2, 3. So before we get started, let's talk about what we mean by 3D space. So 3D space means in order to identify a point in that space, you need to have three coordinates. So we'll call them the x, y, and z coordinates. And together they make what we call an ordered triple. So we're used to calling a point in the regular just x, y coordinate system an ordered pair, but since this has three coordinates, we call it an ordered triple. So sometimes I mess up in my discussion and I call them ordered pairs. But if there are three coordinates, we're talking about an ordered triple. So if I was to draw 3D space, I could say my x-axis, let's draw in this orientation, then my y-axis in this orientation. So this is basically a piece of paper on a table, if you will. Then the z-coordinate, the z-axis, will rise up perpendicular to the tabletop, so we can draw a 3D space. So if I were to plot a point in 3D space, so let's say I wanted to plot the point 2, 3, 8. So I would go out in the x direction by 2, and then I would go out in the y direction by 3. So I have to go parallel there. And then I'd go up in the z direction by 8, so perpendicular. So I'd wind up here. So if this is the point D, I would be here. So sometimes it helps to draw a vector from the origin to orient yourself to space. So I'm out there in space somewhere at that point D. All right, so that's how you would plot a point in 3D space. Now how about a plane? So here's a very basic equation of a plane. X plus y plus z equals 1. So if I wanted to draw a plane or orientation to help me out with the visualizing this, I would plot my x-intercept, my y-intercept, and my z-intercept. And just like when you're plotting the intercepts for any other 2D shape, 2D graph, you zero out the other coordinate and you can see where you cross. All right, so these are the 3 points for my x, y, and z intercepts. So I'm going to put those on. So I'm at 1 here, here, and also here. So I can draw a piece of my surface here. So my surface is right there. So it extends to infinity, but it does give you an idea of where it lies in space. Now, if I wanted to plot another point on that, so let's pick a point. So the reason I know this point is on my plane is that if I plugged 1 here, 2 here, and -2 here, I'd get 1 plus 2 is 3, 3 plus -2 is 1, and that would satisfy my equation, so therefore I know this point lies on the plane. So let's go ahead and plot it. So I've got to go 1 in the x, and then 2 in the y, and then -2 in the z. So it's roughly down here. So I've got a point on my plane, so let's just make my plane a little bit bigger. It's down here Let's extend my surface out a little bit. So that point is further on down on my surface. Let's move it up. Okay, so there's that blue dot on that surface, so my plane extends on down that far. Okay, so this is exactly what the fancy graphics programs are doing in order to figure out where to put these points. They've got a system of axes perpendicular to one another. They got a planar equation, and then they're trying to figure out all of the ordered pairs or enough ordered pairs to plot in order to draw a reasonable looking surface, a smooth surface. Now, when we're solving 3 by 3 systems of equations, we're basically using the elimination method here. And these same 3 rules apply as to how they did in the 2 by 2 systems of equations. The first example says solve this system of linear equations. So I've got a 3 by 3 system that I'm going to solve using elimination. And since I've got 3 variables, I've got to eliminate the variables one at a time in order to be able to solve this. So I'm going to start by eliminating the x first. And I'm going to do that because I can see this lone x here that's going to make that pretty easy to use. So the first thing I do is I multiply equation 1 by 3. And I'm going to do that so that when I add it to this equation, I'll have a 3x here and a negative 3x here, and the x terms will drop out. So I'm going to multiply equation 1 by 3, and I'm going to rewrite it 3x minus 6y plus 9z is equal to 21. Now I'm going to take these 2 equations, this one and this one, and I'm going to write them down like that. And I'm going to add them together so that the x terms cancel out. So those cancel out. So I'm left with negative 5y plus 11z equals 16. Now I'm going to do the other equation on the bottom and get rid of the x term in that one. And the way I'm going to do that is going to utilize that same first equation, except now I'm going to multiply it by the opposite of this 2 here, so that would be negative 2, and I'm going to do the same steps. So I'm going to multiply by negative 2 this time, and I'll get this equation right here. All right, now I'm going to write this equation and this equation. I'm going to follow this same procedure here. So I wrote them down, and I can see that these x terms are going to cancel out again. So if I add the terms, I'll be left with 6y minus 5z equals negative 11. Now what I have are 2 equations here with y and z. So I can solve those simultaneously to figure out what y and z are. So let me write those together. So now I'm going to work on this smaller system here and find out what y and z are. So I can rewrite using the first equation. I can solve for y, and I'll get y is equal to 11/5 z minus 16 over 5. Now I can take this expression for y over here and replace y in this equation, and now I'll only have one variable, z, and I can solve for z. So I substituted in my y, and now I distributed it out, the whole equation. Now I'm going to clear that 5 out of the denominator by multiplying the every term by 5, so I don't have to work in fractions. Alright, so I got the denominator cleared. Now I'm going to combine like terms. So I've got 41z is equal to 41, so z is equal to 1. So I've found z now. Now I need to go back up and find the equation where I had already solved for y. So let's see, that's right here. And if I put 1 in for z, I should be able to get y. All right, so I substituted 1 in, so this is this equation here. Carried all that through, and I got y is equal to -1. Now I need x, so I need to go back up to the top here to find an equation that has x, y, and z in it, so I can plug in y and z. All right, let's go ahead and use that top equation right here. X minus 2y plus 3z is equal to 7. Any one of those three equations will do. So I wrote the equation down. I substituted y and z into the equation. I simplified, and I get x is equal to 2. So I found that these three planes intersect at a point. I have one solution. All right, here's another example. I'm going to carry through the same way. I'm going to eliminate one of the variables out of two equations and use those two equations to solve for the other two variables using the elimination method. So I'm going to use the x's again. So what I'm going to do is that I'm going to multiply, and remember there's many ways that you could do this. This is just the way that stands out in my mind. I'm going to multiply this equation by -4, such that when I add it to this equation, I'll be able to eliminate the x's. So if I multiply the second equation by -4, I'll get -4x plus 12y minus 8z is equal to 32. So I'm writing this equation and then this equation, and I'm going to add those two equations together, and the x's are going to drop out. So I'll be left with 13y minus 7z is equal to 49. Now before I forget to say something about it, you've probably noticed that I'm putting a little line through my z's, and I would appreciate it if you guys got into the habit of doing that. This is something I learned in college. Professors always said you need to put that little line in there because everybody's z's otherwise going to look like a 2. All right, so get into the habit now that we need z's in all these equations to put a little line through your z so that we can tell the difference between a 2 and a z. All right, now I'm going to eliminate the x out of the other pair of equations. I'm going to use the middle one again. If I multiply the middle equation this time by -5 and I add it to this equation, then the x's will drop out of those two equations together. So my second equation here becomes minus 5x plus 15y minus 10z is equal to 40. So I wrote those two equations out. So I've got this one here and this one here, the one that I multiplied -5 by, because I want these to drop out here. So I'll be left with a y and a z term in these two equations. So here I'll get 13y minus 7z is equal to 45. All right, so now I'm left with these two equations with two unknowns, and I can solve those two equations simultaneously. So I'm going to solve these two equations simultaneously. So let's solve one of them for y. So let's solve the first one for y. So I'll have 13y is equal to 7z plus 49. So dividing by 13, I'll have y is equal to 7 over 13z plus 49 over 13. Now I'm going to take that y expression and plug it into this equation where I have a y to solve this system here. So I'm plugging it in. So I substituted it in for y. Now I'm going to simplify that. And you can see that these 7z's are going to cancel out. And you'll have a false statement at the end here. So this is a false statement. So you're going to conclude that you have no solution. When you get a false statement, your conclusion is no solution. So that means there's no places, no points where this set of planes, 3 planes, is going to intersect. Here's another example. So on this one, I'm going to do much the same thing. I'm going to work with this easy x right here to get rid of the x term in both of these 2 equations so I can solve a system of 2 variables and 2 equations to find y and z. So the first thing I'm going to do is that I'm going to multiply this equation by -5 so I can add it to this equation here. So I wrote them both down here. Now you can see that the x term is going to drop out here, and I'll be left with this equation right here. Now I'm going to go back and use this again. So I multiplied the same equation by -4 to get this, and I added this to this equation right here, and I can see that my x term is going to drop out. So if I add the other terms, I'm left with this equation right here. So both of these are in terms of y and z, and now I can go ahead and solve those 2 equations simultaneously. All right, so we've got these 2 equations right here now. They look the same. All right, so you can see that they are the same equation. Now let's just pretend it's not that obvious and go ahead and solve this system through using the same set of procedures. So I would solve this first equation for y in terms of z. Then I would take this expression here, wherever I have a y, in this equation and replace it with this expression here for y. All right, so then if I go ahead and continue on through the steps, you can see that the 8z's are going to cancel out here, and you're left with an identity that says -18 is equal to -18. So if you're left with an identity, that means you've got infinitely many solutions because these 2 are in fact the same line, right? All right, so if you have infinitely many solutions, that means your planar solution is that all 3 planes are intersecting in one line. Okay? So what we do next in this situation is we solve for the relationship between the 3 variables and report that as an ordered pair XYZ. So I'm going to show you how to do that next. So we're going to find what we call a parametric solution for this infinitely many solutions system here in terms of z. Okay, and you have some problems like this in your homework set where they ask for it in terms of z. Sometimes a dummy variable is used, but if you're specifically told to find it in terms of z, we'll just do it that way. All right, so what you do is you say z is equal to z, and that's where you start. All right, so you pick a z. Then you find an equation that you've already established for y in terms of z. So we already have this one here already figured out. So this one is y in terms of z. So here's your expression for y. So I'm going to make my little setup here. So we're starting out with z is equal to z. So you pick any z. Then your y coordinate would be this expression right here. So I'm going to put that in place of the y. The only thing left is we need to know how to figure out the x coordinate given a z coordinate. So we want an expression for x also in terms of z. So we got to go up further to find one with an x in it. So let's go up to this top one here. Here's one that has an x, a y, and a z in it. We can use this one to figure out an equation that says x equals to the rest of the stuff. Okay, so let's use that one there. All right, so I wrote it down. So I'm going to use this top equation here. I'm going to substitute y here, where I've got a y. And then, of course, I'm just setting z. So z is just z. Now I'm going to work this out so it says x is equal to whatever it equals to on the other side. All right, so I just did the math there. I substituted the y in, and then I just went ahead through all these simplification steps. Finally, I have an expression for x with a z in it. All right, so now I can go ahead and put this up here in this spot right here, and I have my solution here written in terms of z. So you can see that there's infinitely many points that can solve this here, that can satisfy this, because you can pick infinitely many z's. Whatever that z is, you figure out the y-coordinate by plugging it in here and the x-coordinate by plugging it in here. So this is a way that we represent that we actually do have a relationship between x, y, and z that's set forth by this set of three equations, but that there's infinitely many points that are going to satisfy this relationship. All right, so here's a case, infinitely many solutions. Now here's a more simple problem where all of the work has been done to reduce this set of equations, this system of equations, into this more simplified form right here. And this is what working with matrices allows you to do. So we call this upper triangular form. And what we mean by that is your top equation has a 1x as your first term, and then you have a y and a z term. Your second equation has a 1y, and then you just have a y and a z. And then your z has a 1 here. So you can see it has this triangular shape here, like this. And this is why we call this upper triangular form. All right, so the way that we solve these is by using back substitution. So we already know that z equals -1. So then we take that z value, and going backwards, we plug that into the second equation, and we can figure out what y is. So I go ahead and I substitute -1 in here for z, and I go ahead all the way through here until I get out y is equal to 7/2. And then the very last thing I'm doing, I'm going backwards, back substitution. I take my y and my z, and I put them into the first equation, and I'll be left with just an x. So I carried out all of that work here, substituting the y and the z values into the first equation, working it all out, and I get x is equal to 8/3. So I have my point x, y, z. So this is a one solution situation. I have one solution, the point highlighted right there. So this is using back substitution, so this requires much less work because it's already in a form that's easily solved. The last thing we're going to do is one type of word problem that I want you to be able to do. Of course, there's many different kinds of word problems that we could study, but in the essence of time, we're going to narrow it down to just the coin problem in 3 dimensions. All right, so this coin problem says, I found 38 coins in my car. There are no pennies, only nickels, dimes, and quarters. There are twice as many quarters as dimes. The total value of the coins is $6.40. How many of each type of coin do I have? All right, so there are nickels, dimes, and quarters. So I'll choose those letters, those variables to represent nickels, dimes, and quarters. Of course, we know that a nickel is 5 cents, a dime is 10 cents, and a quarter is 25 cents. We know that. No pennies involved here, otherwise that would be a 4x4. All right, so we have 3 variables that we need to find. If I have 3 unknowns, that means 3 variables, I need 3 equations to figure it out. So if I only have 1 or 2 equations, I won't be able to figure out what my 3 variables are. So I must have 3 equations to figure out 3 unknowns. All right, so let's write 3 equations. So the first piece of information says I found 38 coins in my car. So that means the nickels, number of nickels, plus the number of dimes, plus the number of quarters has to equal 38. So that's one equation. All right, we need another equation. All right, the next sentence says there are twice as many quarters as dimes. Okay, so we can write an equation out of that. So that means we have more quarters than dimes. In fact, we have 2 times the number of quarters. So the number of dimes times 2 has got to equal the number of quarters. So that's what we mean by there's twice as many quarters as dimes. So if you had 5 dimes, you'd have 10 quarters. So twice as many quarters as dimes. So that's another equation, but we still need another one. So we have another sentence here that says the total value of the coins is $6.40. So $6.40. So remember, we don't want to work in 2 units, dollars and cents. We only want to work in cents, since we already know that we've got 5 cents, 10 cents, and 25 cents. So this is 640 cents. So we can write an equation that says the number of nickels times 5 cents plus the number of dimes times 10 cents plus the number of quarters times 25 cents all has to add up to 640 cents. So now I have 3 equations that I can solve simultaneously to figure out these 3 variables. So what we can do is we can notice that this little short equation here will help us out because we already have Q in terms of D. So wherever I have a Q in these 2 equations, I can write 2D. Then I'll have an N and a D in this equation and an N and a D in this equation. I can solve those 2 simultaneously for the other 2 variables. All right, so looking at equation 1, I'm going to say N plus D plus replacing Q with 2D equals 38. And looking at equation 3, I'm going to say 5N plus 10D plus 25 times Q, which is now 2D, is equal to 640. All right, so now I'm going to solve these 2 simultaneously. So I simplified those 2 equations by combining like terms, and now I have these 2 equations here. So I can take this first one here and solve for N. So N is equal to 38 minus 3D. Now in the second equation, down here, wherever I have an N, I can replace that with 38 minus 3D. So I replaced N in this equation with 38 minus 3D, and now I can go ahead and simplify that. Now I can combine like terms. So if I simplify all the way down, I'm going to find out that D solves to be 10. So I have 10 dimes. So then if I have 10 dimes, I know from this equation that I have 2 times 10 is equal to 20. I have 20 quarters. All right, now I need to find the number of nickels. So I need an equation that has N in it and also D and Q. So I would have to go up to the top here. So here's this equation here. So this one will work. So I could say N is equal to, so I had to move over here. I'm running out of downward space. So solving for N and substituting in there D and Q, I find out that N is equal to 8, so that my number of nickels is 8. So my solution is I have 10 dimes, 20 quarters, and 8 nickels. So that adds up to, let's go back up to the top here, that adds up to 38 coins. And this equation is solved, is met. And then if I substitute it in 8, 10, and 20, and you can prove this yourself, that all adds up to 640 cents, which is $6.40. Okay, so our solution is this right here. So that is all we're going to do with 3x3 systems of equations. I hope you took good notes, and you should be ready to tackle the homework problems now. Let me know if you run into any problems.